Right, what I've got set up here today is a VSD which I've powered through a double wound toroid. It's being fed through the circuit breaker. I've got a run signal connected to it and a potentiometer for the speed reference. And then one of the phases, the U phase, I've got going through a current transducer which uses a LEM module inside. I've got that connected to my scope. So on this side I'm feeding it to 12 volts, and that is the high voltage side coming out of the drive going through the current transducer. So this is galvanically isolated inside, so what's going to the scope on this side is isolated. Okay, so also I've got this earthed over here, so this thing is also at earth potential, so this whole setup is safe as long as you don't go near the output there and the stuff over here, but it is floating as well. Now on the output over there, I've captured the waveform. Now that is the current waveform over there. So we're looking at current through the motor windings over there. So what you're seeing is a sine wave. You're not seeing the PWM, the voltage waveform that comes out of a VSD that we're all familiar with. So if I zoom in on that, one can actually see the PWM ripple in the current over there. Okay, so that PWM carrier is at 3 kilohertz. That's what I've got set up on the VSD at the moment. Now voltage wise, we I'm looking at 130 millivolts. Now the current through this motor at the time when it was running would be about half an amp. That's what this little motor is rated at. So if I go back over here, let's look at the current and I'll give it a run. You can see that we've got half an amp over there, like so. Try and keep my fingers away from the camera lens. So when I run the scope, like that, there you can see the current waveform. There is noise on it, but we're not worried about that at this stage. So there one can clearly see the PWM. Like so. So the sinusoidal current waveform is what replicates the waveform if this were running over, well, direct on line straight off the mains. Your mains voltage looks like this, and your current waveform would look like that. Now because of the PWM, this looks like that over there. Let's go back. The voltage PWM, as it increases the voltage, causes the current to increase, and the current is what produces the magnetism through the motor. Okay, and that's how VSD works. So that's what the current on the output actually looks like. It looks like a sine wave, but when you look at the PWM, you just see vertical lines, and the on time is what determines the voltage and the amount of current that flows through the motor windings. So if I turn that down and I'll stop it, you can see the frequency slow down. Now if I turn the pot right down and I'll start it up, there you can actually see the PWM. Now there's obviously some noise being injected into my wiring and stuff here. Wrong knob. So there's your PWM over there. Now that. So the drive is currently still running. So there you can see the frequency come up. And that's it. Now as you can see, the current is staying constant. That's because this is an induction motor, so your magnetism needs to be constant in order to have your rotor magnetized. Okay, so the voltage coming out of the drive is actually coming down in relation to the frequency. It's called your VF curve. That's your voltage to frequency relationship. So if you measure the voltage coming out of the drive, you'll see it coming down. Now if I get a multimeter, I can actually show that to you. Let's put this here. You can see it. Like so. Move the camera a bit. Okay, there's your voltage coming out. So we are currently running at 16 Hertz. So as I take that up to full frequency 50 Hertz, you see we get to 240. But if I slow right down, you're going to notice at 0 Hertz that we've still got voltage over there. And that's because of the current needed to magnetize the motor, which is what's needed to keep it spinning at low speeds in order to produce full torque, in order to get your performance that you want from a VSD out of it. So that's why you notice this current waveform doesn't change while I change the frequency, and that's very important. You want to keep that constant. Okay, if that changes throughout the speed range of the motor, you know you've got a problem with your setup of your VSD. Your starting voltage or your end voltage may be wrong. So you could end up with one of two situations. Sorry about that. We either have too much current in the beginning or too little, or you have too much current at the end or too little. So you want to keep that linear. Now you have what's called the boost in the lower RPM ranges. So if I turn this down like that, what I'm going to do, show you how I set the boost. Go in here to menu 5, and I'll put it into that's your carrier frequency. So it was actually 666 hertz, not 3 kilohertz. Sorry about that. 1 where was it? Let's go to menu 0. Auto fixed boost, that's 3%. So if I knock that down to 0, let me get a tongue tester. Alright, I'm back with a tongue tester. Let's see. Alright, there's a tongue tester over there. So that is let's move that light away. Like that. 0.8 of an amp. The frequency we're running at the moment, 4.8 hertz. So if I turn my speed pot right down, okay, there we can see it. So I've got 0 boost at the moment. Now I'm also looking at that over there. You can see that the current is low. So if I go back into my boost over here, now let's move the cursor. You can see that the current has come up, and you can also see it on the scope. Now as you bring the speed up, that will taper off. Now that determines your torque at low RPM. Now that varies from application to application, how much you want to mess around with that. Not all loads require a lot of starting torque. Cranes, hoists, extruders, mills, that sort of stuff, they need a lot of starting torque. Quadratic law applications like pumps and fans are an example of an application where you don't need starting torque. In fact, you want low boost or low VF, voltage to frequency relationship, at low speeds to save energy, which is what a VSD does for you at low speeds, is it reduces the magnetizing current in the motor because you don't need the torque because of the square law of torque requirement of a fan or a pump. That's why they're good for saving energy when you control air or liquid flow by reducing the speed of the motor. And that current over there is what you're reducing, which is your energy consumption of your motor. So when you don't need the torque, you reduce that current over there, and it saves you energy. So I thought this would be an interesting talk. It got into a bit of a ramble as usual, but it's interesting as always. You now get to see what that current waveform on the drive looks like, and it's a sine wave, and that's what produces the magnetism inside the motor, is the current flowing through the windings. So even though the PWM on the output of the drive is all jagged, because that's how you control voltage with the drive, it's pulse width modulation, it's either on or off. The current waveform is what's doing the work for you. So that's it. I'm going to wrap it up over here. I'm going to turn all of this stuff off. I hope you found it interesting. It's something not everybody gets to see, and I hope you enjoyed my little setup over here. Got this nicely set up. Got the transformer over here. That's a double wound 250 VA toroid, and current probe over here going to my scope. Now if I set this up, if I turn that off, I'll set that to capture the peak, we should see the inrush into this transformer when I turn it on. No, it didn't catch it. No, it's too quick. But I could actually hear it. You might have heard it yourselves. But that, going back to this waveform over here, when you turn a transformer on, you could be turning it on, applying voltage at any point through through the main cycle. Now what happens, cause an avalanche of stuff, if you turn it on at this point over here, what happens is that current starts flowing through this half cycle, and then current flows through this half cycle and is unsymmetrical. So you briefly get DC current flowing through your transformer, and that then results in your inrush into the transformer, and that's actually the noise that you hear, is that brief DC current that flows through the transformer when you power it up. So that's why you got to size your protection for your transformer, that it allows for that brief surge of current when you power up the transformer and magnetize it, because it's going to be higher depending on where you catch it in the half cycle. Obviously if you catch it at the zero crossing point, nothing happens, but anywhere else you briefly cause DC to flow through your transformer. Now generally one gets away with it, but if need be one can employ what's called a soft start for the transformer, where you power it up through resistors first, and you then bypass the resistors after a few seconds, and that will limit the inrush current. One can also power up a soft starter through a phase controller. One can soft start transformers. It's an uncommon practice. It adds a lot of cost and complexity, and generally it's not needed. But that's where what's called the inrush into a transformer primary comes from. Right. I think I'm out of stuff to talk about here. So a fun little one. I was setting up playing with it earlier today and finally getting around to making the video for you. So here it is. Thanks for being here, ladies and gentlemen. Take care till next time. I'll see you next time for more stuff. Cheers.